Hello, everyone, and welcome to episode 4 of the Cisco Optics podcast, where we talk about optics for networking. Have you ever wondered why pluggable optics exist? Have you ever wondered what acronyms like QSFP, LR4, FEC, and PAM4 actually mean? My name is Pat Chow, and I'm a product manager in the Cisco Optics group. In this episode, I finish a conversation with my colleague, Ray Nearing. He explains to me how a lot of these came to be, starting from the days of 1 gigabit GBIC all the way up to today's 400 gig QSFP DD. This is the final part of a 4-episode conversation with Ray. In this episode, we get into complexity trends and coherent optics. Check out the notes section for a detailed breakdown. Ray Nearing is a colleague of mine in the Cisco Optics Product Management Group, and over the years he's held senior management positions at other companies in the optics space, companies like AT&T Microelectronics, Lucent, JDSU, Agere, Optium, and Lightwire. He's got a lot of experience. He's seen it all. For more information about Cisco Optics, go to cisco.com/go/optics, and check out our blogs at blogs.cisco.com and search on hashtag Cisco Optics blog. No spaces and no hyphens. You can find our YouTube playlist by going to youtube.com and searching on Cisco Optics. And if you find this podcast helpful or interesting, please subscribe and give us a review on Apple Podcast, formerly known as iTunes. We're also on Spotify, Google, Amazon, Stitcher, and SoundCloud, and a whole bunch more platforms. And now, join me as I talk with Ray Nearing.
The market decided to go to a different modulation scheme, which is called PAM4. And so what PAM4 has, instead of just having a 1 and a 0, or one, an on and an off, you have, some intermediate levels as well. So essentially, you've got a 0 level, a 1 level, a 2 level, and a 3 level. So you've got 4 levels of information in that one bit period. And so what that allows you to do is to operate at roughly the same bandwidth as a 25 gig lane. It's more susceptible to noise because now you've essentially cut your dynamic range down. Mm-hmm. But it doesn't require you to necessarily use a new generation of CMOS. So you could use what was being used at that time, which was 16 nanometer or whatever the technology was at that time. You could actually get 50 gig SerDes out of the ASIC. And then there were new ASICs that were coming out that had 6 and 12 terabits of bandwidth available.
But now that you're doing something with multiple levels, not just 2, you can't use the traditional binary devices, right? You can't just saturate an amplifier. You have to hit the intermediate levels as well. Was that a fundamentally new thing to do?
Well, to be honest, PAM4 technology has been around for a long time, and these kinds of schemes have been around for a long time. So if you look at how modems work and that type of thing, they were using some of these more advanced techniques to get as much bandwidth across whatever type of link you might have for other applications. So certainly modems use this technology. Mm-hmm. So it wasn't exactly brand new. And so,
but it's not a digital thing though, right? At this point, it's essentially an analog amplifier that you have to build. No?
Yeah, I guess that's to a certain degree that there's an element of truth there. And then there's also other techniques that are being used to sort of equalize and using now forward error correction that kind of compensate for some of these things as well. So, before when it was NRZ, you might use forward error correction for some applications where maybe you need a little more margin in your specification on the optic side. So you're trying to compensate that. So for 100 gig CWDM4 or SR4, to get the kind of margin that you would like to have in those links, people started to use FEC in those applications. Mm-hmm. So now what you're saying is, well, now I have to use FEC for this electrical interface. So you're seeing, other techniques being used. You're trying to stay within the bandwidth of the technology that you have on the SerDes side, but to get the kind of the error rates that are required within sort of the constraints that you have at that point in time, you're starting to use some of these other techniques, like again, like forward error correction. So now, for 50 gig interfaces, everything uses forward error correction with these PAM4 type of signal technologies.
And the algorithms were defined by IEEE, right?
Yeah, so the IEEE, looked at all kinds of different, techniques for equalization, and they came up with whatever their standards are. And so there's a standard amount of equalization that they use at 50 gig as well as the FEC.
Now, what about the timing of all the different pieces coming together? Was it any different with QSFP-DD? Because, like we were saying, there's no 400 gig CFP, right? We went straight from QSFP28 to another QSFP,
right?
That has the advantages of the backward compatibility, but technology-wise, it seems like we've skipped over some steps that we had to go through in previous iterations.
Well,
is that because everything's coming together all at once?
Well, the market started to work on these problems in 2015, 2016 timeframe, because we knew we had to get to another speed. Mm-hmm. So, I think there were some other form factors that people talked about. But as far as the number of lanes and the electrical SerDes that folks wanted to use, pretty much everybody went to the 50 gig signal technology and using PAM4 modulation. But they had to increase the number of lanes. So part of the reason that QSFP-DD was chosen was they extended that rear connector to have 2 rows of contacts instead of a single row that QSFP Plus and QSFP 28 had. And that gave them the flexibility to kind of leverage those 4 lane or those 8 lanes of 50 gig into a 400 gig signal.
Now, just to clarify, we've been talking up to this point about IEEE defining the optical standards, and then you mentioned CWM4, which is an MSA. SFF does the form factors standards. QSFP-DD is a little different though, right?
Well, QSFP-DD was an MSA, so that's how it started out. So there's a website called QSFP-DD.com, and all of the interfaces for all of the specifications around the form factor are there. Now, the small form factor, the SFF has. I don't think they've taken on the QSFP-DD as a specification, but a lot of the things that are leveraged, let's say, for like the definitions for the codes. So the codes and things that are used in CMIS and how the module advertises, what its capabilities are and that type of thing, are defined in the SFF. So whether it's a 2-kilometer product or a 2-kilometer interface or a multi-mode type of device or a single mode type of device, all of those. So there's some cross.
So their role is still very important, even though they don't officially release that spec.
Right.
And then how about the optical specs, the optical interface specs?
So initially, what was happening was there was an MSA called 100 gig lambda that started as sort of kick off, these optical interfaces for 100 gig per lambda type of specs. The IEEE actually started off with 50 gig lambda specifications way back in, I'll say, 2015, 2016 timeframe. but eventually started
know
to
that.
adopt. Yeah. So you had products like LR8 and
okay.
SR8, SR16, I think was one of the early ones. That one is actually 25 gig. Again, trying to leverage the 25 gig technology that was available at the time. But eventually they started to adopt some of these 100 gig per lambda products, technologies for FR4 and,
And they're
LR4
adopting,
and so on.
I mean, they're adopting a lot of the specs that are defined in the MSA, the 100 gig lambda MSA, right?
Yeah. So a lot of them were, so the FR4 was one that they adopted, and actually the IEEE had already adopted by that time the FR8 rather. So there was a whole series of 50 gig per lambda interfaces that the IEEE had initially put together.
Okay, you said LR8 and SR16 were IEEE's earlier 50 gig based.
And also FR8. So FR8 was a standard as well. But again, I don't think FR8 is very popular at this point. I haven't seen very many requirements for that.
Okay, so they're adopting FR4, you said, and I know that they're doing 100 gig single lambda, right? FR1 and LR1.
Yep. So DR is an IEEE was the first one that was put together, and then FR and LR were part of the 802.3 CU, I think. So that one's in its final stages of adoption, and as well as the 400 gig versions of that as well.
And so now that we have this ecosystem of single lambda 100 gig standards, we have the benefit of this interoperability between 100 gig platforms and 400 gig platforms.
Exactly, in the breakouts, breakouts.
Yeah, I mean, we both talked about this a lot. A lot of people, right? Okay, so we've landed on QSFP-DD. It was initially defined. The form factor was defined by an MSA.
Right.
The early optical specs, at least for 100 gig per lambda, were defined by another MSA. It's moving over to IEEE. It sounds like things are just moving really fast, right? And on top of that, there's also another trend, right? You mentioned FEC even at 100 gig for like CWM4 and like SR4. The complexity, so like going from 1 gig to 10 gig was all about just increasing the speed of the optics and the SerDes, right?
Right.
Other than the data rate, everything else looked kind of the same. NRZ, just NRZ, right?
Right.
Now we're adding FEC, we're adding PAM4. Even at 100 gig, I know that there's more complexity in the module just in terms of just the timing, because there are certain components like CDRs that are just a little more complicated than in a 1 gig SFP. So what I'm getting at is, let's talk about CMIS, because my understanding of CMIS is it was born out of the recognition that these pluggable modules are just becoming more and more complex. And the old style SFP, where you just have an EEPROM with some static fields to identify, the speed, the reach, that approach isn't going to cut it anymore, because we're having to add so many, I don't want to say like higher level features. Maybe that's not the right word.
Well,
just more complexity, right?
Yeah, well, actually it is, because what's happened now is you're starting to have the ability to have pluggable coherent modules, and which is sort of the next step.
Okay. So
for 400 gig, now the OIF had been working on a standard for coherent, first at 100 gig and then at 200 gig, and then they started tackling the 400 gig standard. And this is primarily for the application they were targeting was sort of this DCI or data center interface where in a region, someone like Google or Microsoft or whoever have a series of facilities that they want to connect together and use and operate as one large data center instead of separate ones. And so the ability to make those connections with a coherent module makes a lot of sense with a coherent interface. But the cost is a big deal for those applications. So
why do you say it makes a lot of sense with a coherent? What is it about coherent that makes...
You can go much further distance at a high data rate. So for 400 gig, the ability to go, let's say 100 kilometers or so is something that they thought was a good idea. And to be able to do it with a WDM network, and those applications are going to drive a lot of volume. So they wanted to come up with something that was standardized, that could be made by a number of different manufacturers. Everyone would be able to interoperate. So generally, up to this point, coherent systems were bookended by the companies that made them. And so what that means is that you would have the same vendor at both ends of a long link, of a coherent link. And whatever modulation technologies or encoding schemes that they used to kind of go over whatever that distance was, they control both ends of that. Where in a multi-vendor operation, you might have one vendor on one side in a data center and another vendor at the other side making the same kind of module, and they have to interoperate. So
is it that the people that were using these bookended systems before saw the pluggable optics on the data side center of the world and said, hey, I wish we could do that too, right?
Well, I think it was actually the end user said, I'd like to be able to leverage the ability to scale and to drive costs down with these coherent links that I can't do in a bookended system.
And those end users have the volume to drive that price down. Is that
exactly
what's happening?
Right. So when you start looking at how they want to use these types of devices, they're going to be able to drive those kinds of volumes, and they want to be able to bring the cost down. The cost of these links generally is pretty high, much orders of magnitude higher than any kind of client link that you might use. So what they're looking at is saying, if I adopt this type of architecture, I can drive a lot of volume, but I can't do it if it's going to be this high-end type of system. So that may be fine if I'm going to go thousands of kilometers between links, from one side of the country to the other. But if I'm only going 50, 80, 100 kilometers, something in that range, I could use an awful lot of these, and I'm not willing to pay the same price for these ultra long haul systems for this what I'll call DCI type application. So the technology for a coherent link now, the DSP technology has gotten to a point where that DSP that makes that coherent signal and decodes that coherent signal can fit inside a pluggable module. And so
so that's a key milestone then.
Yeah. So now the technology got to a point where the CMOS technology has gotten to a stage where now I can fit all that stuff inside something the size of a pluggable module.
Size, meaning physical size, but also power, right?
Power dissipation as well. So now those customers are saying, hey, I'd like to be able to plug this thing directly into a router instead of going through a transponder or a long haul system. And if I can do that, I can now scale the use of this coherent module across all these different applications that I have.
So once you plug it into the router and you don't have to use a transport system, you're 100% in IP land, right?
Basically, yeah.
So that's just a lot easier, right? It's just one less thing to worry about.
Well, I'm sure there's plenty of things to worry about, but the idea here is that you're enabling this sort of new architecture, and that's that's part of the reason why Cisco bought Acacia.
Yep. Okay, so what does this have to do with CMIS, which is how we got onto the topic, right?
So now you've got this thing that's pretty complicated that potentially is inside that module. And not only do you have FEC, but you've got all these other algorithms to be able to go long distance. And so now there's other information that you might want to try to understand about.
Wait, sorry, what other algorithms? Like what other things?
Be able to compensate for dispersion. There's.
So is there handshaking or some initialization steps where you communicate between the two ends before you bring up the link to measure the dispersion and all that?
No, they don't. Well, I don't know. There might be. That I'm actually not sure about. But there's differences in how these modules can be used. Now it's a WDM module. It can be tuned to a bunch of different wavelengths. You probably want to know what your OS&R is in that module. So now there's a whole bunch of other things that you might be interested in trying to find out. So how do you initialize that module? Things like that. So
it's not only the fact that it's coherent, it's also the fact that you're in DWDM, in a DWM system.
Well, there's a lot more that you want to know at that point. And so there are other things that people want to monitor. So in those longer haul systems where you're actually going outside the data center itself, you may want to try to understand how much error correction you're doing in that link. And is your link degrading over time somehow? Am I going to have to worry about that link later on? It hasn't failed yet. I'm still getting a good error rate, but it may be doing a lot more work for some reason. Am I getting error bursts somehow for some reason? So you have a lot of other things that you need to worry about, or that you may want to know about what's happening inside that module. So, and also people want to understand more about the traffic as well. So there's probably some back and forth between that ASIC and the module that customers want to try to understand what's happening to the actual traffic.
So what is CMIS and how does it help monitor all these things?
Well, CMIS is essentially the common management interface. And it's all of the sort of
like a command set.
Yeah, it's basically the command set on how that module, on what controls that module, and all the things that are happening inside that module. And so it basically defines, how to bring the module up, how to shut it down, what are all the functions inside that DSP that it's. What is it doing? What are the status of all those things? Since that module is so much more complicated today and could even include all this coherent type information, there was a new standard that was put together that was called CMIS. And so at this stage, I think they're currently at CMIS 4.0. And I think they're going to release a Rev 5 soon if they haven't released it already.
Oh, really?
So, yeah.
Okay.
But it's complicated, and it's a lot different than the old QSFP modules operated.
And and this is already for QSFP-DD?
Yes, and it currently all the modules that Cisco sells comply with CMIS 4.0 or higher.
Okay. So, a lot of times what we at Cisco we like to point out is all the testing that we do, even for SIPs and QSIPs, they're complex enough that they never pass the first round of tests. We always have to make tweaks because there's just enough things going on, enough things to go wrong that inevitably something's going to happen. So now that we're talking about FEC with CMIS and all these other, it just seems like it's getting all this complexity is just inviting more potential problems that requires more attention to detail.
Yes.
Yeah, I guess I'm not really asking the question. I'm just kind of thinking.
The modules are much more complicated. There's a lot more going on inside the modules. There's more information that people want to understand about that module. And when you think about all the things, all the functions that are happening there, it's not really that surprising. You've got entirely new modulation schemes, both on the electrical side and the optical side. So, none of these things are easy. And, I'm sure that, many customers have already recognized some of those problems. I mean, those were, we've seen a lot of issues in firmware and people understanding what CMOS is and kind of getting it right. And we won't release those products until we've gone through them in gruesome detail to make sure that they operate in all of our systems over all the conditions that they can actually be used over. And, that does require a lot of testing, and it also requires a lot of interface and back and forth with the vendors themselves.
And I think just expertise, right? I mean, this stuff is not simple.
Right.
And you need people who know what they're doing to test it right?
Yeah, and there are new things to look at. So, it's not like the old QSFP Plus. It's not just leveraging what you did before. It's all brand new. And so we've seen a lot of issues with a lot of the vendors that we've been working with, and we've worked through a lot of those issues on the products that we've released.
All right, so I think we did pretty well. We went all the way through coherent QSFP-DD, which is ZR plus, right? What is next on the horizon?
So what I would say is it's going to be, the next generation of SerDes. And so probably what you're going to see is 100 gig SerDes. Certainly the OIF has worked on their version of a spec for 100 gig SerDes. And the IEEE has been working on it for a while now. I think it's in the 802.3 CK. So they've worked
that's
on
a PAM4 base that can feed directly into the 100 gig Lambda.
Yeah, exactly. So, what you're going to see is 800 gig or 2x400 gig type modules come out first, and then eventually 800 gig type modules in a QSFP-DD form factor. And the QSFP-DD MSA has come up with a spec for 800 gig modules as well. So there's a website called QSFP-DD800. And essentially what they've done is they've taken the standard QSFP form factor, QSFP-DD form factor, and they've tweaked the specs a little bit so that the module can handle 800 gig.
So is it the same MSA group, just a different website, or is it a different MSA?
It's a subset of the current MSA. So a subset of the companies got together and said, let's work on 800 gig. They've done that. And the specification that they've come up with is essentially an addendum to the QSFP-DD specification. So it's you really have to kind of combine the two for that requirement. But people have signed up for it, and I would expect to see modules in a year or two that are operating at 800 gig.
Cool. It's a never-ending story, I think.
Yes.
Wow. Ray, I think we covered a lot of ground. I really appreciate your time. These are things that I kind of knew something about, but was always curious about the details. And to put it all together like this, for me, is really gratifying. So really appreciate it.
Great. Well, hey, I'm happy to help out.
That was the final part of my conversation with Ray Nearing, my colleague from Cisco Optics. Thank you so much for joining us, and I hope you found it as interesting as I did. If you did, subscribe to this podcast. You'll get to hear the other 3 parts. You get to hear a bunch more podcast episodes coming up. And since this is a new podcast, we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of networking and optics. And leave a review on Apple Podcast. It used to be known as iTunes. Now it's called Apple Podcast. We're also on SoundCloud and the Cisco Podcast Network and all major podcast platforms and some minor ones too. Also, check out the Cisco Optics blogs at blogs.cisco.com and search on hashtag Cisco Optics blog, no spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you so much for listening. This is Pat Chow, Product Manager at Cisco Optics. Until next time.